live. So currently, look at this. All of the kitty cats are upstairs. So let me show you the hallway. I'm waiting for them to come down and greet me. They just had their lunch and they promptly went upstairs, and who knows when exactly they will join me again. But here we are for our Sunday live. Hi Rosie, how are you? How are you, Rosie? Thank you for joining. Thank you for joining. Thank you for joining. You'll just have to see me for the moment. How's your Sunday going? I am good. Rosie's saying I'm good. So I need to share the live. Otherwise, our friends might not be able to find our live. But let's try again to see if Fuji Suji Baji will come down or not. Fuji Suji Baji. Suji Baji. Suji Baji. No one's coming. It's okay. Give it a second. They'll be down here. I'm actually going to take this opportunity to see if I can make some coffee. But generally, if I start to touch the dishes and go into the kitchen, that the kitty cats definitely come down. So soon you will see us all. So hold tight and enjoy the live. And thank you for being here. And if you're seeing this as a video upload later on, definitely give us a comment. Say hi in the chat. And thank you for being here. Let's get this party started. I'll put you right here by the window where the kitty cats usually are. Suji Baji. And Rosie, tell me about your day. It's so funny because usually they're down here, and when I want them down here, then they're upstairs. And actually what happened is that it got really cold in Boston. That's part of this, is it's upstairs, has lower ceilings, and so it stays kind of warm when the heat is on. And downstairs, even though the heat is on, it can actually be a little bit colder. So they're all extremely cozy up there. That's sort of the status of this. Oh, hello. Welcome, welcome. Thank you for joining. Thank you for joining. Thank you for being here. How are you guys doing? Hello to everybody. Fuji Suji. You'll see when I touch the kitchen stuff, like if I make any noise and they realize that mom's in the kitchen, they will come down. So don't worry about that. Thank you again for joining. We will get this party started. So it's just me right now, but thank you so much for joining. Really good to see everybody. Oh, what is that? Oh, that's on my screen. Okay. I thought there was something on my face. Maybe there is, but at this time, I'm a little blinded by the sun here. And I'll get my coffee started because these people, these kitty cats are taking their time. Fuji Suji. Suji Baji. What's that? Is that a... Look at that. I'm drinking coffee right now. Look at this. Look at this. As soon as I fix their bowls, suddenly there is a teleportation of kitty cats. Look at this. Look at these people. Do we know these kitty cats? So I just touched their bowls and they heard that noise so well. They heard that sound. I just fixed the bowls and put them in the proper place, and now there's 3 kitty cats all of a sudden. All of a sudden. Now who's had their lunch already? Who's had their lunch already? But whose bowls did Mama touch to put them in the right place, and then now who is here? Oh, my babies. Such a cute baby. Rosie is saying, I'm drinking coffee right now. Oh, good. I'm about to do the same thing, Rosie, but I thought I'll get the live started and get it all settled, so that we can get settled here. Oh, wow. Who is this? Baji Baba Shona. Baji Baba Shona. Baji Baba Shona. Hi. Oh. What a view, Baji. Hello. Hello. Is it me that you're looking for, is what Baji has to say to his audience. There is my Suji Mama. Suji Bablu. Suji Bubli. Oh, Suji Bubli is going to use the bathroom. Go ahead, Suji. And where is my Fuji? Oh, I think Fuji has gone to the bathroom to inspect the litter robot. He has been keeping an acute eye on the new toilet. Actually, let's take a look at that. How is that going? I cleaned the bathroom yesterday, so hopefully you don't see. Oh, look at that. Fuji is monitoring the litter robot. I think that he basically interrupted the cycle. Oh, good thing I fixed their bowls, because their food just started to get released and fed. So here we are. Let me fix their bowls further, because now Fuji doesn't have a bowl. Here you go, Fuji. Here you go, share it with Fuji Baji. Oh my gosh. There's a lot that goes on here. There's food falling, there's bathroom being checked, there's an automatic robot trying to do its cycle. The automatic robot cycle is interrupted when one of the kitty cats go and touch it. But that's okay, because that's all right. So Little Robot just told me that it completed a clean cycle. So I think in between the kitty cats kind of using the toilet and interrupting its cycles, it kind of finishes the cycle. And I'm just glad that it, so far so good, touch wood, you know, everything is working so far and well. So, and I'm happy that this auto feeder has also worked. At one point I broke it, but because it's kind of strange, the timing of this worked out because the little robot was able to finish its cycle, because over here we are busy now with the foodie. So anyways, thank you all for joining. We'll just do a casual chat today. We won't do, I don't think we're gonna do a book reading today, but we're gonna be chatting and catching up. So good to see everybody. I'll put you guys down over here so that you can see the kitty cats doing their thing, and I'll share the live in the meantime and make a coffee. Oh my goodness. Okay. We are live. So yesterday I kind of missed my live. I got busy. So I hope that we make up for that today by chatting and catching up now. And Friday we had a pretty long live, and we caught up on physics topics on Friday. It was actually pretty nice, really amazing discussion with the unification theory, Einstein's unification theory, as well as quantum mechanics. I might do a little bit of that today depending on who's joining. We might continue our quantum mechanics discussion, but I realized that I need to prepare some materials to introduce the topic more. So I'm gonna do that this week actually, but right now it's just a casual chat. Just chatting right now, just chatting and hanging out. Okay. So thank you for being here. Join us. Let me say that. Yeah, so we are just gonna be doing a casual chat and hang out at this time. Oh wow, look at that. Look at what Baji did. He pushed the auto feeder and got the last bits of his food out from the tunnels of the auto feeder. I don't know what else to call it, the feeding tunnels. He's very good with technology. He's the first one to kind of embrace any new modern technology that enters the home. And in fact, he has tried most of our technology in the house. He can turn on and off the shredder. He can turn on and off, well, he doesn't turn it off, but he can turn on the keyboard piano and then play the keys of it. So he's done that too. And he can obviously push this auto feeder and get more food out. Fuji at one point figured out how to open the auto feeder and get just one piece of food out and then close it, like not shut it tightly, but close it so he can still reach into it again and act like it's closed so that I don't know that it's been actually opened. So all of this is done by these kitty cats. Baji, are you leaving? Are you leaving us? Wow. Wow, Baji. I think the kitty cats want to go upstairs. Maybe we'll have to go join them upstairs soon here. But I don't know how the Wi-Fi will do upstairs. That's the only issue. Because usually the Wi-Fi does not, it becomes very poor signal upstairs. Maybe we'll have to use data to see them. Baji! Wow. I think, you know what the situation is? Today is cloudy. The window is right here. They love the window. They spend a lot of time at this window. But today it's kind of cloudy. Look at that. There's the sky over there. It's kind of cloudy. It would be sunny at this time usually, but it's cloudy today. So they don't want to be at the window. And instead, they want to go upstairs and cuddle in the bed. I didn't make my bed, and so they love it. They're in all the nooks and crevices of the blanket, and in fact, I have to change my sheets. So maybe we will go upstairs and look at them doing that. Oh, wow. What a day. This is going to be different. This is going to be different, huh? I might just accomplish this though. Maybe I'll go change my sheets and you guys can also see the kitty cats. Yeah. But give me a second. Let's keep chatting here for a second because I have to make my coffee. Otherwise, I will be rather unhappy this afternoon. So give me a second. I know the kitty cats are not at the window right now, but maybe you can still enjoy the window for a second. Sorry. Just hang tight. We'll go upstairs in just a second. Okay? Hang tight, please. Get settled. Get settled for a nice afternoon of fun times and cozy kitty cat with blankets. We will travel upstairs soon. We will pack our luggage for the upstairs very soon here. So that's what we're gonna do because that's where they are. That's where they've decided to go. It's really to do with the weather and how everything is looking and feeling down here because see it's cloudy. If it were sunny and the window was opened, Like if it was warmer and the window was open and the sun was coming in, I think they would all be at the window. That's their usual. So, anyways, I'm gonna make the coffee and then go upstairs. They changed the plan today. So I'll keep telling you about the stuff we covered on Friday too. We covered some interesting things, which actually made people's brains bend. And if any of you from Friday are here, you can chime in and talk about that. People were a little bit like, okay, this is too brain bendy, and we need a moment, and let's continue this next time. So here we are. Now the brain bendy thing happened because, well, quantum mechanics is a little bit brain bendy. The part that we were covering. Okay, bye Rosie. Rosie said, I will be, wait, I can't see it. I will be on later, bye. Okay, thank you for being here. Let me just real quick tell you about the part that we were on. For the people who are still here, thank you so much for being here. This was the part that we were on. This is part 3 of Einstein's Cosmos, Unfinished Picture. And even though it was a little bit of a difficult topic for some people, nevertheless, it was very interesting, and we learned a lot about some people, some new characters in the story of the 1920s and 1930s in science. And these new characters are called Schrödinger and Dirac. So we did not know too much about Schrödinger and Dirac in this book so far, but now they've appeared, and they're contributing very interesting and exciting things to quantum mechanics, and also doing relativistic quantum mechanics. That's what Dirac did, and that's kind of how things were going at the point where we left off. So if you're interested in that, we will keep on covering that today. If not, we can also just kind of hang tight and go see the kitty cats in a little bit. But I'll let you give me some feedback on if you're interested in the physics topics today or not. Okay, and here is the book. Hopefully, I don't know if you can see it. Let me see a picture. Here's the book. So let me know if you're interested in covering this book. If so, I will. And I will continue the discussion. And I have my own notes as well on quantum mechanics. If not, I will take you upstairs to see the kitty cats in a few minutes. Okay? So let me know. Let me know. Yay. I had some water. That feels good. Hello, my friends. Hello, my friends. If you were here for the Friday live too, let me know, because if you were not here, then I'll probably repeat some of the things I said on Friday for that topic. But if you caught it, then I will not repeat it. Okay? So, or sorry, I don't know why I moved it. I don't think this is a very good view. I think upstairs, the only issue is I'll definitely have to use the data, because for whatever reason, I always lose signal, or the Wi-Fi does not really work upstairs. Which is kind of a blessing because it means that upstairs I don't really use the internet much. We can have offline time. You know? Let me bring the phone over here actually so that I can see any comments that you write. Oh, hello. Hi. Hello, my friends. Hello, hello. Look at this. This is their full. Oh, actually, this is kind of interesting. Looking at the living room through the kettle. Look at that. Here's some refraction for you. So this is where they usually hang out, and apparently nobody wants to hang out here today. As in, I mean the kitty cats. Thank you for being here, at least in my living room. This is the living room and I'm in the kitchen right now. It's all very close together, which is rather nice actually. I don't really miss having a home that is so big where the kitchen and the living room is like a mile apart. Not really, but you know what I mean. Everything is compact here in Boston, so that's why you can still hear me from the kitchen. But because it's warmer upstairs, because the heat was just on. The heat was just on and it's warmer upstairs. And so all the kittens have gone upstairs and usually we're over here. Oh, you know what I will do? I will also show you the book we were reading. I'll leave it out here so that you can see and give me some comments on whether you want to hear about it or not. Okay? Because usually I've been covering this on Friday for the Physics Friday, but I'm also happy to cover it on any other days too when we go live. But I think the Physics Friday is now a staple. And whatnot. So we just kind of take it as it goes. Take it as it goes. Take it as it comes. I don't know. Thank you for liking the live. Oh, hi, Baji. Look who has joined me. Look who has joined me. My precious child. Oh, my baby. Hi, Shona. কি হয়েছে বুবলাই? Oh, Fuji is here because of the food. He wants to smell my croissant. This is a croissant from a bakery near me that I like very much. And he always wants it. He can't have it, but he wants it. You can't have it, Baba. It has chocolate. Oh gosh, this microwave. The croissant has chocolate. Of course, he can't have any. And the coffee, of course, none of this. None of this is for you, Fuji. Hey, Baba, ki kocho tumi ki khacho? Oh my God, what are you doing? I think he's sniffing for some of my milk powder as well. He loves dairy. You love dairy, don't you, Baba? He loves dairy, so he's like just seeing if there's any scraps of milk powder anywhere that he can sniff out and have. It's quite keeps me on my toes, let's just say. Look at him. Look at him. He's looking around everywhere for this. Baba, korona shona. Chole asho, dike chole asho. Baji's here too. I didn't see you there, Baji. Look, Baji's here now. Baji's here now, and Fuji's here now. I think all the noise I made with making my food here has brought the kitty cats down. Baji, Fuji are here. Yay! Baji! Baji, 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 Baji. Baji and Fuji have braved the downstairs, even though it's considerably more comfortable probably upstairs. More cozy, soft bed, although the couch is pretty soft, but it's just more comfy up there, isn't it? Isn't it? You can see Baji like this. Can you see him? I think you can. You can see Baji like this. How about that? You can see him like that. Fuji, Karnashana, Sergao. Look at your face, Baji. Baji's like, I want the croissant, but you can't. It's got chocolate, and also in general you can't. In general you can't. Fuji, no. Oh, Fuji, I'm sorry, but I put you down. Put you out of the counter. Hi, Suji. Suji Mama is here too. I think I see from the corner of my eye a Suji Bubli. Is that right? Or wait, who is this? Who is this? Is this Fuji? Trying to eat my food? No way. No way. No way. Fuji. Shoro Babu. Karna. Shona. Fuji Shona Karna. Let's go this way. Let's turn. Left and then right. Let's turn. Let's turn. Let's turn. Baji, your face is so funny. I can see Baji's face on my iPad because I can see the live on my iPad, and your face is so funny. Your face is so funny. Shata Shona. Oh, Baji, your face is so funny. Hi. Oh. Hi. He's usually very upset with me for not sharing my croissant. Baji's saying hi to everybody from his vantage point. Hi. Baji is doing chin positivity. He wants to say showing your chin is a positive thing to do. This is Baji's face when he watches me eat croissant. Oh. I heated it up too much. No, Fuji. Baji's holding the phone now. He has a very long arm to hold the phone with. His arm is like a selfie stick. Isn't that right, Baji? Baji, is your arm like a selfie stick? Is it like a selfie stick? Baji, is your arm very long? Yes, it is. Baji says, yes, my arm is long. Fuji is, of course, right on me. I finished eating my croissant and Fuji's over here sitting extremely close to me, giving me an atomic scale of space. Fuji, do you know about the Pauli exclusion principle? We can't exactly be in the same exact spot together. But Fuji doesn't believe in Pauli exclusion principle. Let's ask Google. Hey Google, what is the Pauli exclusion principle?
On the website chem.libretexts.org, they say, the Pauli exclusion principle states that in an atom or molecule, no two electrons can have the same four electronic quantum numbers. As an orbital can contain a maximum of only two electrons, the two electrons must have opposing spins.
Got it, Fuji. We must have opposing spins. So I think Fuji is saying that he does obey the Pauli exclusion principle because he has a different spin than me. And so it's quite all right. He's not breaking physics by giving me close to no space while I eat my croissant. He wants to say that our fermions are extremely complementary to each other, and therefore we can You know what I should do? I should write a kitty cat story that's based on physics. You know what I should do, Baji? You know what I should do, Baji? I should write a children's book for kitty cats or with kitty cats, and I should make it a lesson on quantum mechanics as well, because the other day I found that it wasn't relativity, it wasn't mechanics, or I don't know, even gravitation or general relativity that made people a little worried. It was quantum mechanics. People are a little bit confused by quantum mechanics because it is a little different, isn't it? It's a small scale. All the subatomic particles are making people a little mad. So I think what we'll do, Baji, I could write a children's book teaching quantum mechanics. Would people read that? I feel like physicists would read that, probably. They could teach their children quantum mechanics with this book, which has kitty cats. Wait, what is this, Baji? Oh, there's a hair in your mouth. Oh, I'm sorry. Baji had a hair in his mouth. It's my hair. My hair is a little out of control in this house, I will say. There's too much of my hair that's everywhere, and we're quite tired of cleaning it constantly. But what about a children's book on quantum mechanics based on kitty cats? Why the frick not? Why not, says Baji. Why not? Baji, will you be the main character in it? Actually, you know what? It should be about Fuji. He's the one who gives me the least space. Not that I'm complaining. I'm quite happy about this. But he's the one. Hi. Hello. I think Baji knows that it annoys me when he tries to eat my food. So he's actually very sensitive. So at this point, he likes to maintain his distance and just watch me from up here on the cat tree because he doesn't want me to get mad, because then he would feel a lack of love. And above all, a lack of love is what he cannot tolerate. He wants love first and then food and then other things, whatever those are. But those are mere perturbations to the main equation of Baji, which is love and food. Those are simply added terms, much, much, much lower importance. Baji, what's a perturbation? Do you know perturbation, Baji? We will cover it on a Physics Friday. But so I was thinking, even though Baji is a main host of this channel, I think what I shall do, it might have to be Fuji. That is the fermion telling the story about how you have to have an opposite spin. You do. You do. Let me write that down. Let me write this idea down that I could write a book on quantum mechanics. Hola. Hola, Baji. Hola. Hey. Ay. Hi, Shona. Tumi Shona. Tumi Shona. Tumi Shona. Tumi Shona. এটা বাজি একটা সোনা বাজি একটা ভালো সোনা একটা ভীষণ ছোট বাচ্চা কত ভালো একটা সোনা কত ভালো কত ভালো কত কাটলি তুমি কাটলি আর ইউ আর কাটল বেবি Baji's smiling. Look at his smile. He's smiling. Baji smile. Baji's smiling. Oh. Ole baba. কত সোনা ছোট ছেলে কত ছোট হাত ধরবে You wanna hold hands, Baji? And look at your face. Your face is too cute, Baji. Your face. Look at Baji's face. I think Baji's about to start snoring. He had his lunch, so he wants to take a nap and snore. Look, he's over here now. Oh, I found a better shelf for you. Whoops, sorry. I found a better shelf for you. Hi, Baji. These angles, man. I don't even think I've seen this angle of my house before. But that's where it be. That's where it be, Baji. That's where it be. Baji is enjoying his perch on this side now. Welcome, welcome. Thank you for joining. Fuji's over there. He's keeping a watch on everything I'm eating, hoping that it's shared with him. I think he'll be the fermion in my book. He'll be a fermion. That's what I should do, is I should basically define out all the types of particles and spin nature and all of that. There we go. It should be like that. It should be something like that. It should be something like that. Puchki chele. Puchku puchku chele. These are very puchku cheles. These are little babas. I think they really love to be here with me. Otherwise, they would be upstairs. I'm gonna do some work on my laptop and chat with you guys as well. I think that's what we'll do in this current moment. Yep, I can see Baji. I can see Baji and Fuji. Fuji kiss time. Fuji. Hi, Fuji. Hi. I have dinner plans today. What about you guys? Do you have any plans? Y'all have any plans for the night, for the evening, for the afternoons? Actually, sorry. I sat down without bringing the phone over here. Oh. Hi, Flowey. Oh, Fuji wants to be on lap. Let me just get the phone over here and the book over here. Sorry. Actually, you know what? We might do a book. We might do a little bit of book reading. I forgot that I said I might do that. Fuji ashbe? Kole ashbe? Come. Come, Flowey. Yay. Fuji's on lap. I'm looking at a message that I missed earlier from my family. Sorry about that. Just making sure it's not anything. Whenever I open my laptop, I see more messages because some of the messages go to my phone and some of them only come to my Mac. So, all right, Fuji, are we ready for some Einstein's Cosmos time? Should we do a reading? Over there is Baji. Over there is Baji. Yes, it can be cozy down here too. When Mama sits down, when I sit down, then it's cozy. When I sit down, then it's cozy. When I sit down, with the blankie. So, here's what I'm thinking. I think I'll do a little bit of a reading. And I will just repeat it again on Friday if you miss it today. Or if you missed something this past Friday, we'll kind of recap and cover some more things. Yes. Yes. How does that sound? Not good, good. Okay. So, we left off on Friday was the fact that we now had something called antimatter or antimatter, however you want to say it. Good. Hi, Ki, my friend. How are you? So antimatter is not anything that bad. It's simply the same particle but with the opposite charge. So turns out because E equals mc squared, really when you take a square root of something, you're actually supposed to put the plus or minus. See how it says plus or minus. So Einstein kind of forgot that his E equals mc squared is really with a plus or minus. Okay? So here's my Fuji Baba, and here is the book. And we were reading about this part, which was actually sort of an important but subtle part. And this is where Dirac gained a lot of importance. Because what Dirac did was take Schrodinger's equations and write them down as relativistic equations. Because remember, relativity is sort of kind of like taking what we knew in classical mechanics and extending it to be relative, where space-time is relative, where mass energy has equivalence, and where the ingredients of general relativity are also maintained, where we learned about the equivalence principle with gravitating frames of reference and things like that, for example. So it's basically possible to take something that's written down classically and convert it to a form that is more relativistic form. It's almost like a correction, if you will. Some things may look kind of very different, but some things may look almost similar, sort of the relativistic form of the same thing, because we're basically making a correction, if you will, a correction that you wouldn't really need in most everyday life cases, but a correction that becomes very important if the speed of light is important in your work and if you need to be more accurate. Okay, so basically if Schrodinger had written down equations for a particle, a quantum particle, say under the influence of a potential well, this could be an infinite potential well or a finite potential well. If Schrodinger was writing down the equations for such a particle, well, you can write down the equation for such a particle in a relativistic way. And that's actually what Dirac did. So we will reread that part a little bit here so that we can recap what we learned here. And that will also further bring the memories of what we were talking about. So we learned about also the Bose-Einstein condensation, by the way. So Shotendranath Bose, actually a scientist from where I come from in India, had done some work, as well. And it's sort of a condensed matter type of work, if you will. Physics has many subfields. Condensed matter is one of them. And he had basically come up with this very odd or interesting state of the superatom. And then it went on to become something which we call the Bose-Einstein condensate. Even the word boson, a type of particle, which light is an example of a boson, is named after this same guy, Shotendranath Bose, B-O-S-E, Bose. That's how we get boson, okay? So we kind of learned about that, and that's sort of taking us in the direction. So Einstein's work is kind of taking a turn at this point, where he's even kind of getting into condensed matter physics, and sort of, I think this was sort of a gateway into quantum mechanics for him as well, in a way. Even though, he's the one, of course, who worked on the old quantum mechanics, which is calling light a particle or a photon. That was him. He won the Nobel Prize for that, figuring out this relationship between light and how when light falls on a metal, it can cause an electric current to flow. And that electric current, it's proportional to the frequency of the light you would use, or the energy of the photon, or the quanta of light that was being used. And all of this relationship giving us photoelectric effect, photons then causing electrons to have to flow with a certain energy or get a current. That is the photoelectric effect. That's how we have solar powered energy, for example, photoelectric effect. And it was an easy to do demonstration, in the sense that you could just change the color or the frequency of the light you were using, and you could see a difference in the power that you were getting out of it in terms of electricity. So he is the one who actually proposed that, hypothesized that, and showed that along with other people as a demonstration, and we got the photoelectric effect. So this is called the old quantum mechanics. In a way, this is sort of easy stuff, because photons are the particles that make up light, or the particle nature of light, sometimes called photons, sometimes called quanta of light, sometimes even called bosons, because photon is a type of boson. These are not the most complicated particles in particle physics. So at this point, there's another whole field of physics called particle physics. Standard model of particle physics might be something you heard about. This is a complicated field with many, many types of particles. Now, it is just in my humble opinion that photons are not exactly the most complicated of the particles. Once you learn about all the particles in the standard model, you may pick a different particle that you consider to be more simple. But in general, I think photons are not the most complicated. So that's why people are kind of saying, as people made more progress in quantum mechanics, and it gave rise to a whole host of different particles, and especially the subatomic particles and the even more smaller particles, the even more fundamental particles that make up our ordinary matter, that gave rise to the standard model of physics. We will get into that later on. It's not really in this chapter, but I wanted to give you a little bit of preview where we're headed in the direction of physics. But because currently we're still covering 20th century physics, whereas more developments in particle physics happened a little bit later. Okay, so that's why you haven't seen too much with say quarks and things like that, because those particles are discovered later. At this point, we've just discovered, we're in the timeline where we've... Hi, Baji, can you give us a little bit of space so that Fuji doesn't get disturbed here? Hi. Oh my God, oh my God, oh my God, oh my God. Baji wants to snuggle as well, but the thing is that you're gonna make Fuji go, and I don't want that. I don't want Fuji to move. He's very comfortable. Oh my God, Baji's sitting right on Fuji. Baji, please, could you pick a spot that is complementary to Fuji? These kitty cats really don't like the Pauli exclusion principle. Anyways, so I wanted to give you a little bit of a preview of the standard model of physics, or particle physics, which will include many, many more particles. We will look at quarks and bosons and leptons and all that stuff, which will come later, okay? Right now, where we are is we've just kind of discovered in the timeline of physics, in the history of physics, where we are right now is we've just discovered the nucleus of the atom, okay? And that's already a big deal. Discovering that the atom was not fundamental, that the atom further broke down into even smaller things, and there was a nucleus, and the electrons are sort of in these orbits around the nucleus, not perfect orbits or anything like what we are around the sun or anything like that, but sort of, yeah, people kind of thought at one point that the electrons were in these little perfect orbits around the nucleus, because even just discovering the nucleus was a big deal, because it meant that atoms were not the most fundamental particle. So that's the timeline that we're in right now in our story. And in this timeline, at this point in the 1920s, late 1920s, Einstein is sort of one of the contributors of the initial effort in quantum mechanics by saying that light is has a particle nature, and that the particle nature of light can be observed. It is called a quanta of light, or a photon, or a boson. Okay, we will move on from this and go to the next part. So, in addition to Bose-Einstein condensation, Einstein was interested in whether his principle of duality could be applied to matter as well as light. So, this is what I was just talking about, the fact that he had discovered that light had a particle nature. So now we're asking the question the other way around. If light can have a particle nature, then can matter have a wave nature? Basically, is there sort of a wavelength of matter, or a matter wave? And what is the description of that? How do we write that down? So turns out you can actually write that down, and there was progress made in this field as well. And we will cover that in the next few paragraphs. So, in his 1909 lecture, Einstein had showed that there was a dual nature to light, that it can be simultaneously, that it can simultaneously have both particle and wave-like properties. Although it was a heretical idea, it was supported fully by experimental results. So, when he had suggested, because remember, when Einstein was working on all of this stuff, because it was in that same year, 1905, so very early 1900s, when he had come up with this photoelectric effect stuff. And there had been some progress in quantum mechanics at that time by Max Planck, remember, but still, calling light both a wave and a particle was a very big deal, because at that time, we had just kind of come out of the whole sort of movement and understanding of light in terms of Maxwell's equations, which was very much giving the electromagnetic wave nature of light, the electromagnetic picture of light. To then call, and then of course Einstein also worked on special theory of relativity, which also embraces, of course, light as a wave and gives us the more true nature of light, and how it, how we can derive from Maxwell's equations that actually the speed of light is a constant in every frame. Those types of things are the special relativity contribution. It's a very big deal. But then to get out of that also that light has a particle nature, and that you can show that with an experiment by just simply, he could actually show this because of photoelectric effect being so possible to demonstrate. This was a big deal, but he showed it with experiment, backed it up with actual results from an experiment, and that's why it was possible. And people had to accept it. And later on, he was awarded the Nobel Prize for that. So, inspired by the duality program initiated by Einstein, a young graduate student, Prince Louis de Broglie, then speculated in 1923 that even matter itself can have both particle and wave-like properties. This was a bold, revolutionary concept, since it was a deep-seated prejudice that matter consisted of particles. Stimulated by Einstein's work on duality, de Broglie could explain away some of the mysteries of the atom by introducing the concept that matter had wave-like properties. So just like light had particle-like properties, matter could have wave-like properties. Einstein liked the audacity of de Broglie's matter waves and promoted his theory. De Broglie would eventually be awarded the Nobel Prize for this seminal idea. But if matter had wave-like properties, then what was the equation that the waves obeyed? Classical physicists had plenty of experience writing down the equations of ocean waves and sound waves, so an Austrian physicist, Erwin Schrödinger, was inspired to write down the equation of these matter waves. While Schrödinger, a well-known ladies' man, was staying with one of his innumerable girlfriends in the Villa Herwig in Arosa during the Christmas holidays in 1925, he managed to divert himself long enough to formulate an equation that would soon be known as one of the most celebrated in all of quantum physics, the Schrödinger wave equation. So this Schrodinger wave equation is basically a wave equation for matter. And later on, it gets updated as we will see in this story. But this is where we're now getting into some of the sort of pioneering work in quantum mechanics. Okay, so pay attention. Okay, Schrodinger's biographer, Walter Moore, wrote, like the dark lady who inspired Shakespeare's sonnets, the Lady of Arosa may remain forever mysterious. Unfortunately, because Schrodinger had so many girlfriends and lovers in his life, as well as illegitimate children, it is impossible to determine precisely who served as the muse for this historic equation. Over the next several months, in a remarkable series of papers, Schrodinger showed that the mysterious rules found by Niels Bohr for the hydrogen atom were simply consequences of his equation. So, in the meantime, Niels Bohr had made some progress with finding features of the hydrogen atom, which is, of course, made up of only one proton. So, it was an important and kind of nice example to learn some properties of this particular element or atom. And he was using this atom to further learn about quantum mechanics. But then Schrodinger, who had just written down the wave nature of matter, had come up with an equation, in fact, for writing down matter waves, if you will, found that actually these can now be merged with whatever Niels Bohr was finding, which was very important because remember, all these theories, if you write down an equation, that's well and good, but if you can somehow relate it to an experimental evidence and back it up with a result from experiment or a real life type of thing, then that's what makes it strong and actually stand the test of time and also get accepted by others in the field, and maybe those other people can also progress it further, and that's kind of how science works. So over the next several months, in a remarkable series of papers, Schrodinger showed that the mysterious rules found by Niels Bohr for the hydrogen atom were simply consequences of his equation. For the first time, physicists had a detailed picture of the interior of the atom. So this is also part of the Niels Bohr work, of course, by which one could, in principle, calculate the properties of more complex atoms, even molecules. So even if the equations are being written down for, say, a simple picture or a simple element like hydrogen, which just has one proton in its atom, but if you can write down the equation for one proton or one atom or one nucleus, however you want to call it, the hydrogen atom is, of course, ideal because it's simple. But if you can write down the equation for something simple, you can then extend it to, something more complicated and even molecules, if you will. It might just be a very, complicated equation and you have to deal with all the math for all these different atoms or protons or whatever at that point. But if you can write it down for one and show it for one, then that's a good start. And that's considered good physics, basically, if you will. Within months, the new quantum theory became a steamroller, obliterating many of the most puzzling questions about the atomic world, answering the greatest mysteries that had stumped scientists since the Greeks. So, progress in quantum mechanics, partly because quantum mechanics is, of course, the physics of the very small, the scales of the atom, or even smaller, like the nucleus, proton. These types of things are difficult because also, of course, observing these things, the very small things is difficult. But as progress was being made in this direction, basically you can start to see if the equations you're writing down are actually working or not. And that's kind of what Schrodinger was doing with the help of Niels Bohr. The dance of electrons as they moved between orbits, released pulses of light, or binding molecules together suddenly became calculable, a matter of solving standard partial differential equations. So Schrodinger wrote down partial differential equations for these atoms, for these, small things, let's say, small matter things. And not only that, now you could start to maybe observe these as well and see if you are right. and also get a physical picture of what was happening basically in the at the quantum level. One young brash quantum physicist, Paul Adrian Maurice Dirac, so now we come to Dirac, even boasted that all of chemistry could be explained as solutions of Schrodinger's equation, reducing chemistry to applied physics. So basically, all of the things we see in chemistry, electron, basically electrons moving around and making new molecules and all of that. It's basically energy exchange happening or energy movement happening between these orbits, or things merging together, hydrogen, oxygen merging together, for example, to make water. All of this is chemistry. Of course, chemists will have much more to say on the topic, but some physicists who study quantum physics and the interaction of energy at that level and electrons at that level may call all of this sort of an applied physics, because you're getting the quantum picture. I would say chemistry as a field is much more than this, because of course you learn much more things in chemistry if you take chemistry. But at the fundamental level, at the level of the electrons and what was happening at the atomic level at that point, it seemed basically like an applied physics field. Thus, Einstein, who was the father of the old quantum theory of the photon, became the godfather of the new quantum theory based on these Schrodinger waves. So this is what I was talking about earlier, because he is the one who gave us the particle nature of light and the photoelectric effect. That is considered the old quantum mechanics. Today, when high school chemistry students have to memorize the funny football-shaped orbitals that surround the nucleus with strange labels and quantum numbers, they're actually memorizing the solutions to the Schrodinger wave equation. The breakthroughs in quantum physics now accelerated enormously, realizing that the Schrodinger equation did not incorporate relativity. Just 2 years later, Dirac generalized the Schrodinger equation to a fully relativistic theory of electrons, and once again, the world of physics was dazzled. So, Schrodinger did not incorporate relativity in his equations because, he was already doing something new. He was writing down the equations for matter waves, for the atom, for a particle, and there was some, math and figuring things out to do there already, and nobody had really attempted to write down equations for a particle in the sense of like this wave equation for a particle before, right? Because people hadn't really this wave particle duality thing was not as accepted, or was not even a thing before photoelectric effect, probably. So at this point, people are being brave. People are asking good questions with regard to the duality of things. They're asking, well, if light can have a particle nature, can matter have a wave nature? This is quite fundamental. This is quite different from how people used to think. And so to then take that further and write down the wave equation for a particle, that's quite something. And that's what Schrodinger had done. So this is the big contribution of Schrodinger and his equations. Hi, Aditya. Good night. Hello. And then here comes Dirac, and he is saying, well, you could even incorporate relativity into these equations and make them into relativistic Schrodinger equations for matter. Why not? Hi, Aditya from India. Very nice. Thank you for joining. Welcome, welcome. So, realizing that the Schrodinger equation did not incorporate relativity, just 2 years later, Dirac generalized the Schrodinger equation to a fully relativistic theory of electrons, and once again, the world of physics was dazzled. While Schrodinger's celebrated equation was non-relativistic and only applied to electrons moving at slow velocities compared to light. So if the electrons that Schrodinger is writing down the equations for move at a slow speed compared to light, then it's okay to write them down as non-relativistic. But if they were to have speeds that are close to the speed of light, then you might want to write them down as relativistic. And in general, if you were going to make them more general, anyways, then relativistic is the more general form of any of these equations. So that's why Dirac took it a step forward, and that's a very important step forward because, of course, it makes the math more complicated. So if somebody wants to sit down and do it, then here's Baji, then why not, right? So that's what Dirac was doing here. Hi, Kayla. Kayla Cauldron's sister Kimmy has joined the chat. I'm back. Oh, very nice. So this is the work that Dirac is now going to do, which is to take Schrodinger's equation forward and further and make them relativistic. So Dirac's electrons obeyed the full Einstein symmetry. Furthermore, Dirac's equation could automatically explain some obscure properties of the electron, including something called spin. So when he introduced relativistic nature to these equations, that is where you get something called spin, which is a fundamental property in quantum mechanics of particles. I missed you so much. Aw, missed you too. We're talking about physics, but thank you so much for joining and have fun with us. Here's Fuji and here's Baji. The boys are with me. The boys are with me. The boys are with me. Oh, Fuji. Yes. This one is Baji. This one is Baji. This one is Baji. This one is Baji. This one is Fuji. Yes. Baji is just like you, right, Kayla? Kayla said at one point that Baji is just like her. So this is where we got spin. So you see how with incremental discoveries and work, and of course it takes a lot of work, it's not a simple thing to just make something relativistic. To write down the equations as relativistic is important work that Dirac was doing. And from that, we got this new thing, a new property of matter or of particles called spin. Okay? We will learn a lot more about this later on, but we will keep going for now. It was known from earlier experiments by Otto Stern and Walter Gerlach that the electron acted like a spinning top in a magnetic field with angular momentum given by 1/2 in units of Planck's constant. The Dirac electron yielded precisely the spin 1/2 given by the Stern-Gerlach experiment. So in terms of electrons in terms of spin, this electron had the spin of 1/2, and kind of agreed with some of the things that these other people had seen from experimentation. The Maxwell field representing the photon has a spin of 1. So this fundamental property spin that we are now chancing upon, that we're now finding, this property spin is different for photons versus for electrons. Turns out electrons and photons are two different types of particles. Actually, electrons are leptons. Some people also call them fermions. And when we meet Fermi in all of this, that's where they will get that other name. But basically, electrons are a different type of particle fundamentally than something, say, like photon. And this is clear as well from this particular property, which is spin, because electron has a spin of 1/2, whereas photons have a spin of 1. Photons or bosons have a spin of 1, okay? And Einstein's gravity waves have a spin of 2. So, with Dirac's work, it became clear that the spin of a subatomic particle would be one of its important properties. So, because we got spin from Dirac's work, as well as it turned out to be something different for these different types of particles, for the electron versus the photon versus gravity waves. These things having different spin also makes them different types of particles, is what the author is saying here. Then Dirac went one step further. By looking at the energy of these electrons, here I'll put the camera on Baji now. Choto chelito, choto. Choto, 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 choto. Choto, 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 choto. Bublé. By looking at the energy of these electrons, he found that Einstein had overlooked. Oh, so this is where we come to the very funny part of this. Sort of funny, but sort of important. And this is sort of where we were when we last talked about this. So look at this. This is very clever of Dirac because it seems he's very detail oriented. And being detail oriented can have big payoffs sometimes. So at this point, Dirac is about to get a very big payoff from being so detail oriented. So by looking at the energy of these electrons, he found that Einstein had overlooked a solution to his own equations. Usually, when taking the square root of a number, we introduce both positive and negative solutions. For example, the square root of 4 can be either plus 2 or minus 2. So because Einstein ignored a square root in his equations, his famous equation, E equals mc squared, was not quite correct. The correct equation was E equals to plus or minus mc squared. This extra minus sign, argued Dirac, made possible a new kind of mirror universe, one in which particles could exist with a new form of antimatter. So this is basically how he discovered antimatter, and it'll turn out to be something that people kind of made a big deal about, but actually it's really not that bad. It's simply the same particle, but its opposite charge, okay? And it's kind of falling out as a solution to these equations once you incorporate relativistic nature to these equations, okay? Once you make them have relativity, basically, okay? So it's not too bad. I think people were worried that they had found like a new type of matter or something like that, or that everything had a antimatter sounded to be kind of intimidating to people. You know, an example would be the positron, electrons, antimatter. The antimatter of an electron is called a positron. It's the same mass as an electron, but has the positive charge. You know, but it's not that bad. It's just another type of particle. Once we get into particles, you will see that there are many types of particles. Thankfully, they can be grouped according to some sort of categories of particles. So it's not like you have to really think about all of them individually. But there are quite a few. So that's why there's a new branch of physics called, particle physics and the standard model of particle physics. So, it's all good. We'll get into it. Strangely, just a few years earlier in 1925, Einstein himself had entertained the idea of antimatter when he showed that by reversing the sign of the electron charge in a relativistic equation, one can get identical equations if one also reverses the orientation of space. He showed that for every particle of a certain mass, there must exist another particle with opposite charge but identical mass. Relativity theory not only gave us the fourth dimension, it was now giving us a parallel world of antimatter. However, Einstein never one to quibble over priority, graciously never challenged Dirac. So he might have stumbled upon it himself, where he basically saw that you got this other type of particle out of your relativistic equations, which was basically the particle, same mass but opposite charge. It also came out of Dirac's work, by recognizing that E equals mc squared is really the plus or minus mc squared. And then also because of the spin stuff, realizing that there is a category of particles which is sort of the anti of the particle, the antiparticle of the particle. At first, the radical ideas of Dirac met with fierce skepticism. The idea of an entire universe of mirror particles that arose from E equals plus or minus mc squared seemed like an outlandish idea. Quantum physicist Werner Heisenberg, who with Niels Bohr had independently found a formulation of the quantum theory equivalent to Schrödinger's, wrote, "The saddest chapter of modern physics is and remains the Dirac theory. I regard the Dirac theory as learned trash, which no one can take seriously." So he did not like, I suppose, Heisenberg, who himself did a lot of work as well. Actually, Heisenberg will come back in this story, I'm sure, because he did something very important. Apparently, at first, he did not take it seriously. He thought it was trash, this notion of antiparticles or antimatter. However, physicists had to swallow their pride when the anti-electron or positron was finally discovered in 1932, for which Dirac later received the Nobel Prize. So thankfully, they discovered the anti-electron or the positron particle quite quickly in 1932. If it had not been discovered experimentally, then this theory might have died very quickly, because I think people were having trouble accepting the fact that all these particles have sort of an antiparticle, sort of a twin with the opposite charge. And it is falling out of the relativistic nature of Schrödinger's equations for matter or for particles. And it's coming from the math, but people were, just because our ordinary matter is made up mainly of, the stuff that we know and love, electrons, people were not wanting to accept that an electron could have sort of a twin called the positron. People didn't see it much in our everyday life. And this is one more example of something where it's in everyday life, but just not as common. So that's why it's just not as known and accepted. And when it's first, proposed, it was not accepted. Heisenberg finally admitted, so when it was actually shown with an experiment that the anti-electron existed, that the positron was a real thing, then he admitted, "I think that this discovery of antimatter was perhaps the biggest jump of all the big jumps in our century." Wow. Once again, the theory of relativity yielded unexpected riches, this time giving us an entirely new universe made of antimatter. So I don't like this wording of the entirely new universe. It makes it sound like there is another whole universe of antimatter. And maybe there is another universe of antimatter, but I think that can be a little misleading. Let's just say that antimatter is something that can exist, but it's not the more common form of matter as we know and love. And it's just something that can happen sometimes in certain interactions and particle physics type of events. It seems strange that Schrödinger and Dirac, who developed the two most important wave functions in the quantum theory, were such polar opposites in their personalities. So yeah, they were very different people, both Schrödinger and Dirac, very different from each other, but they both contributed to quantum theory, especially with their equations. And because, if these equations helped us to understand matter and particles in a completely different way, we didn't really have wave equations for particles before Schrödinger, and we didn't have relativistic wave equations for particles before Dirac. So these people gave us a way to formulate and write down mathematically the mechanics of particles. How does a particle behave? How does a particle change its position as a function of time? Let's just say, more specifically, sort of what people are trying to write down in physics is generally something like this. What is the position of the Earth as a function of time around the sun? Is sort of a classical mechanics type of equation to write down. What is the position of a particle, say, within an atom? Like what is the position of, say, the electron within an atom under the influence of, or because of being in a potential well within the atom, because there's also the nucleus. What's the position of this electron, say, in a hydrogen atom as a function of time? That's sort of a quantum mechanical type of equation to write down. But pretty much when you hear about equations and what physicists are trying to write down, it's safe to assume that it's probably something to do with the position of something with respect to time, as a function of time. That's what basically these equations are, fundamentally. Some form of that, So just like people were, think about the times of like Galileo and Newton and all those people in the past, like in the 1600s, 1700s, 1800s, we didn't really know so much about small particles and atoms and electron within the atom. We didn't know about those things. We knew about the heavenly bodies. We could see that, there's the sun, there's the moon, like what is the moon's orbit around the earth, right? One might want to write down an equation for that. Such an equation, as an example I'm giving you, is a classical mechanical equation. But if you go into the very small picture of atoms and electrons and nuclei of atoms, and you want to know what is the position of the electron as a function of time, then that's more of a quantum mechanical field of study now, okay? And those equations are going to look a little bit different. And people suggested at this time that they might have a wave nature. Particles may have a wave nature. When you go down to that level, that scale, that smallness, then that particle has a wave nature, and then you might want to write down the equation for that, and Schrödinger did. So this is the big contribution of these people. Schrödinger gave us a way to write down the equation for a small thing, like a particle, like literally an electron within a hydrogen atom or something like that. And then Dirac gave us the relativistic form of that equation. So these are the biggest contributions of these people. So quantum mechanics is literally for something like that. It's basically writing down the mechanics or the movement description, let's just say, oh, look at Fuji, for something very small, okay? So if you're ever confused about what in the world is quantum mechanics, what are people trying to even do? They're trying to predict the position of a small, tiny particle as a function of time. Probably. There's probably other things too that they are trying. But most fundamental question of a physicist is probably this. They want to predict. They want to be able to say something about the, about the position of a particle, about what it will do, and what governs it, what forces or what fields or what is the way to write it down, basically. What energy, is there a way to equate its movement with some kind of like energy thing or what? That's the equation. So soon physicists at every institute on this planet struggled to learn the strange, beautiful properties of the Schrödinger and Dirac equations. So once they became a thing, of course, people have to learn about it. That's the thing. As more and more physics gets invented and discovered, the students have more to learn. However, for all their undeniable successes, quantum physics still had to grapple with a troubling philosophical question. If matter is a wave, then precisely what is waving? So because he wrote down a wave equation for a particle, and this particle, most basically could probably be thought of as an electron. More specifically, it could be the electron within a hydrogen atom, because why would we want to make our lives hard right away? The simplest atom is the hydrogen atom. It has a proton and an electron. We don't even want to get into helium at this point. We just want to understand, say, now that we know that hydrogen is made up of atoms, this atom, in fact, has a nucleus. There's an electron around that nucleus. The nucleus is a proton, and that's it, thank God. There's an electron in there too, making this atom. And the electron, its position is not fixed. It changes its position as a function of time, with respect to time. We want to say something about this electron. Please, can you please tell us how this electron's position will change as a function of time? What kind of thing governs it? How do we write down an equation for this? Is there like an energy here that we incorporate? Is it fixed? Is it always the same position? No, it's not. It's a wave-like. There is a wave-like nature to this. Okay, so let's write down a wave equation for this. But electron is a matter. It's a particle. It's a material. You're saying that you wrote down the wave equation for an electron, Schrödinger, but what is it what's waving? What's the thing that's waving, That's what people were asking at this point. This is the same question that had haunted the wave theory of light. Remember? They were so haunted, remember, in a previous chapter, they were so confused about the light having a wave nature, or the sort of electromagnetic wave being light, and the electromagnetic waves forming light. Remember how they were worried and wanting to find ether, a way for light to travel, basically, for a wave to travel, blah, blah, blah. And that gave rise to Einstein's special theory of relativity, where he came up with more insights about light. But anyway, now they're asking, if there's a Schrödinger wave equation for a particle, what about it is waving? So, this same sort of question had haunted the wave theory of light, which gave birth to the incorrect theory of the ether. So people had come up with theories for ether because they realized that light is electromagnetic wave, electric and magnetic fields are waving, and that's light. But any wave might need, at that point they thought any wave needs a medium, and they came up with the incorrect theory for ether as the thing that allows light to travel. But in this case, they still don't know exactly what is waving. A Schrödinger wave is like an equation, a Schrödinger wave is like an ocean wave, and eventually spreads out if left by itself. So it's sort of a wave that spreads out. It's like an ocean wave. If left by itself, it'll kind of taper out. It'll kind of taper out. It's not going to keep on going. It's sort of an ocean wave. It spreads out if left by itself. In other words, with enough time, the wave function eventually dissipates over the entire universe. So, because he's in this equation, there's time, there's space, there's the electron, there's energy, and the wave function that he wrote down for the electron, for a particle, really, but we could imagine the electron being that particle. It's an ocean wave type of thing. The nature of it is like an ocean wave. It spreads out if left by itself. And unless you make it, wave again, it spreads out over time. So with enough time, the wave function eventually dissipates over the entire universe. But this violated everything that physicists knew about electrons. So here you are, Schrödinger, writing down an equation for the electron, which we know is part of the hydrogen atom, because let's just say we know only one element right now because we have our hands full. Let's just forget about everything above hydrogen in the periodic table and consider just hydrogen. It is one atom. It has an electron. It has a nucleus, which has a proton. That's it. But we know that the electron pretty much stays in the atom. It's not spreading out over the whole universe. And people even thought that the electron was in these perfect little orbits around the nucleus. And pretty much in chemistry experiments, you can even see some of this and observe what was happening within an atom. So if you're saying that your equation is giving that it spreads out over time into the whole universe, it's almost like the electron can just go anywhere. Like, what does that mean? Like, what do you mean? This atom is there, the proton is there, the electron is there. There is an equation now for the electron, but it's not making sense. Subatomic particles were believed to be point-like objects that made definite jet-like streaks, which could be photographed on film. So these jet-like streaks were even photographed on film, so they kind of had an idea for how this electron, moved around the nucleus. Thus, although these quantum waves had near miraculous success in describing the hydrogen atom, it did not seem possible that the Schrödinger wave could describe an electron moving in free space. In fact, if the Schrödinger wave really represented an electron, it would slowly dissipate and the universe would dissolve. So it's almost like I was saying, this wave dissipates over time. So people were confused and scratching their head, like, what do you mean physically, though? This equation is nice and good, and it's making sense, and it's giving us a good description, but wouldn't that mean that everything just dissolves over time? If this wave is just kind of dissipating over time? So something was terribly wrong. Finally, Einstein's lifelong friend, Max Born, proposed one of the most controversial solutions to this puzzle. In 1926, Born took the decisive step, claiming that the Schrödinger wave, so this is 1926, still pretty early on in the century. Born took the decisive step, claiming that the Schrödinger wave did not describe the electron at all, but only the probability of finding the electron. So thank God, it's just the probability of finding the electron. Because if you're saying that you have an equation which is giving us a wave equation for the electron in free space, and of course there's a nucleus which influences the electron, and you have an equation and it gives us how it behaves, how its position changes over time, but it's a wave that dissipates over time, then we would expect everything to just kind of dissipate and dissolve. And why would this atom even be a thing and the electron still be there and stuff like that? But then now Max Born comes in and says that actually that wave nature that we wrote down for the electron or a similar particle is really the probability of finding the electron, probability of its position versus time. He declared that the motion of particles follows probability laws, but probability itself propagates in conformity with the laws of causality. So again, the motion of particles follows probability laws, but probability itself propagates in conformity with the laws of causality. So this is where we might see later on that the probability of finding something, the probability of measuring something might be affected by how we measure it and the fact that we measure it in itself. And this is where we will find more things later on. But this made more sense, right? Because it would have been really bad if the electron itself were to just dissipate over time. If the probability of finding the electron dissipates over time into the universe, then that's better, because that means that there is a higher probability, hopefully, of finding the electron closer to the nucleus and form the atom that we were observing in real life. Because if you have an observation of an atom and an observation of electron in it, and you kind of know that the electron makes this type of movement around the nucleus, sort of, from the observation, but then your equation is saying that the electron should just dissolve into space, then that's not very good. So now this is better. It's saying that the probability of this electron's motion is what is waving, is what is giving us the wave equation. That's the wave. That right there is the wave. In this new picture, matter indeed consisted of particles, not waves, which is good. We know that matter consists of particles. Thank God. That sounds good. But there is a wave equation for matter, but really that wave equation describes the probability of the position of matter, not the probability of the matter, if you will. The markings, so this is what people have to get used to when they study quantum mechanics. You are writing down equations for the probability of things, not the things, because if you wrote down the equations for the things, that would be bad. That would be hard. That's not really what's waving. Thank goodness. It's not that that's waving. The probability of that is waving. The markings captured on photographic plates are the tracks left by point-like particles, not waves. But the chance of finding the particle at any given point was given by a wave. So if you had experimental observation of the particles leaving tracks on a photographic plate, and you saw kind of what it did, and you knew that it didn't just dissolve into the universe and go away, dissipate over time, like get farther and farther away from the nucleus or something, just like the electron goes into like infinity or something, that would be weird, because we know that atoms are a thing. And electrons are in the atoms. The electron is within the atom. It's within a certain spatial distance within the atom. So if you said it just goes away, then that would be wrong, because we know physically that that's not the case. But now we are saying it's the probability of the position of the electron that is being given by that wave equation. So the chance of finding the particle at any given point was given by a wave. The chance of finding the particle. What does that mean? Chance of that position of the particle as a function of time. So all this stuff, we're still just talking about the position of a particle as a function of time. That's what this equation is. Position of Fuji as a function of time. Position of Baji as a function of time. See how their positions are still quite near me. If their positions were said to dissipate over time into the space, that would be kind of weird. That would be like, that's not really the case. We can see observationally they're right here. But what is being given by the wave equation is the probability of the position of Baji here and the probability of the position of Fuji here. The probability of the position of an electron in the atom as a function of time. Okay? That probability is given by a wave equation. It can be part of a wave. And that wave equation, of course, is a type of wave equation given by Schrodinger's wave equation. So, chance of finding the particle at any given point was given by a wave. More precisely, the absolute square of the Schrödinger wave represents, actually, so you have to take an absolute square, actually, of the Schrödinger wave, represents the probability of finding the particle at a specific point in space and time. Okay? Probability of finding, so the probability of finding a particle at a specific point in space and time, that's given by Schrodinger's wave equation. And you actually have to take his wave and square it, absolute square it, to get the actual number for the probability. Whereas if you write it just as the wave equation, then that gives you the wave of it. But if you want the number, then you need to take the square. Thus, it did not matter if the Schrodinger wave spread out over time. So yeah, as I was saying, the position of Baji and Fuji here, the probability of finding them here could be a wave, but they're here. They're not going into the space, thankfully, thank God, touch wood. Because so if I had a wave equation for them and their position with respect to time as a function of time, and it said that it just dissipates over time, that would be pretty weird. It wouldn't be the reality. But if you say that wave equation is giving us the probability of finding them at a given position, then that could be something we could accept. So that's why it did not matter if the Schrodinger wave spread out over time. So, because we know that the Schrodinger wave spreads out over time, and this was a problem. But it didn't have to be a problem now. It simply meant that if you left an electron by itself, over time, it would wander around and you would not know precisely where it was. All the paradoxes were now solved. The Schrodinger wave was not the particle itself, but represented the chance of finding it. Because, this electron, if it's left by itself, then yes, it could wander about. But if it was near a nucleus, then the situation would be different. I think the neighbor just came in. That's why they're startled. Oh, look at Poji Baba. Oh, you're such a Shona. Poji, baby. Actually, give me 1 second. I have to text my... Okay, 1 second. Okay, thank you. Sorry. So, basically, it's a good thing that it's the probability of finding that electron that's being described by the wave equation, because it means that if nothing is keeping the electron in an orbit, then the electron was allowed to just wander off into space and dissipate into... The probability of it wandering off was given by this equation. So it could either be close to something or not close to something, depending on the energy and what's binding it. But basically, if it says that over time it could just wander off, really it's the probability of that happening, which was being given by the wave equation. So it did not matter if the Schrodinger wave spread out over time. It simply meant that if you left an electron by itself, over time it would wander around and you would not know precisely where it was. All the paradoxes were now solved. The Schrodinger wave was not the particle itself, but represented the chance of finding it. Werner Heisenberg took this one step further. He had agonized endlessly with Bohr over the puzzles of probability infesting this new theory, often getting into heated arguments with an older colleague. One day, after a frustrating night of grappling with the question of probabilities, he took a long stroll down Failed Park behind his university, constantly asking himself how it was possible that one could not know the precise location of an electron. How can the location of an electron be uncertain as claimed by Born if you can simply measure where it is? So there's two things going on. You can measure what's happening to the electron. You can take those photographic plates. You can see where the electron is in that sense. But also Max Born is saying that at any given time, it's really the probability of finding the electron that we get from the wave equation, meaning that its exact location is uncertain. But on the evidence, you could see its exact location. So what was that? How could you kind of resolve these two things? Then it suddenly hit him. Everything became clear. In order to know where an electron was, you had to look at it. This meant shining a light beam at it. Looking at something means that you're using, for example, light to look at it. I could imagine there's other particles that one can use to look at something, look, quote unquote. But say if you want to visibly see something, what you're doing is you're using light, an interaction of light to see or measure that thing, which itself has significance. So, in order to know where an electron was, you had to look at it. This meant shining a light beam at it. But the photons in the light beam would collide with the electron, making its position uncertain. So if you shine a bunch of light on the electron, that means that at the quantum level, photons were interacting with that electron. So that would probably knock it off a little bit or move it a little bit. So then it would make its position uncertain. In other words, the act of observation necessarily introduced uncertainty. So just because you observe something doesn't mean that it's not uncertain. In fact, if you observe something, you introduce uncertainty. You introduce a level of change, basically. You're changing something by observing it. He reformulated this question into a new principle of physics, the uncertainty principle. So this is why I said earlier Heisenberg will come back, because his uncertainty principle is very famous, which states that one cannot determine both the location and the velocity of a particle at the same time. Because you just looked at it means you changed it. Now that part is uncertain. And if you know where it is, then you don't know its velocity. You can't know both because there's uncertainty. There's the whole probabilistic nature of the wave that describes the wave nature is really about probability of finding the particle, and observing it changes it. And so the uncertainty principle says that you can't have both the position and the velocity. More precisely, the product of the uncertainty in position and momentum must be greater than or equal to Planck's constant divided by 4 pi. This was not just a byproduct of the crudeness of our instruments. It was a fundamental law of nature. So it's not just that our instruments are bad and that's why this was happening. This is really just the nature. It's literally that you've used photons to look at the electron, and the photons affect the electron. So by using photons to measure something about the electron, you're making something change. So whatever you just did changed it. And so you can't know both the position and the velocity at the same time. Even God could not know both the precise position and momentum of an electron. This was the decisive moment when the quantum theory plunged into deep, totally uncharted waters. Up to then, one could argue that quantum phenomena were statistical, representing the average motions of trillions of electrons. Now, even the motions of a single electron could not be definitively determined. Einstein was horrified. He almost felt betrayed. He almost felt betrayed knowing that his good friend, Max Born, was abandoning determinism and one of the most cherished ideas in all of classical physics. So, this deterministic nature of classical physics, this is another way in which classical physics and quantum physics are different. Classical physics, by far, is more for our everyday life and scales and sort of scales of the heavenly bodies, for example, or us living our life in houses and cars and roads. That's classical physics. Then there's quantum physics of the very tiny. Physics of the very tiny is different, but also it's different in the level of determinism. Deterministic nature is more of a classical thing. Being okay with not being deterministic but probabilistic is a quantum thing. So in quantum mechanics, you have to accept that you cannot be deterministic at all times. It's not like classical physics. In classical physics, people who are very classical physics oriented would have difficulty with this. But that's why this is quantum physics. This is not the same. Okay? They're generally taught in different years so that you're not completely crazy by the end of the year. I took classical physics, for example, in undergrad second year and quantum in my fourth year. Of course, in grad school, they're taught at the same time, and you do lose your mind at some point. In fact, when I took my quantum final in grad school, of course, I was a poor grad student, so I didn't really party much or drink alcohol much or anything like that. But after my quantum final, I actually drank a little too much and got very, very sick because it was a very big deal that I took my quantum final. Anyway, that's a side comment. Determinism states, in essence, that you can determine the future if you know everything about the present. So this whole situation of, okay, we know, for example, it can be predicted where the moon will be later today. Because we know where the moon was yesterday, we can predict where the moon will be today. Because the laws governing the motion of the moon, at least at the classical physics level, which is good enough for the most part, is such that it doesn't really affect the moon's, figuring out. It's predictive, it's deterministic. Because we know it yesterday, we can predict it for today or tomorrow or even years into the future. This is deterministic physics. Classical mechanics or classical physics is like this. But if you do the same thing, replace the moon with an electron, because the electron is so tiny, the fact that you're measuring things about the electron will affect it. And there you have kind of changed it. So you cannot actually predict something else about it now. For example, if you have tried to figure out where it is, position of it, well, you've done something to give it a, extra velocity probably or something, and now you don't know its velocity. There is uncertainty to do with its speed. So it's just not as easily predictable and deterministic as say something like the moon or a classical object. So you just have to accept that there are classically obeying physics and objects, and there are quantum mechanically obeying physics and objects. Small things different than large things, okay? Just kind of have to accept that with quantum mechanics. Once you kind of accept these things, it becomes very easy, actually. Quantum mechanics, I think, is actually easier than classical mechanics. It can feel a little bit mind-bendy, but it's not that bad. Classical mechanics actually has a lot more, it can be very difficult. The equations you need to, do the space stuff, I mean, it's well understood, but it's kind of like a lot. It can be gory as in it can be complicated. It's not like quantum mechanics is complicated and classical is not. Classical it can also be complicated. So For example, Newton's great contribution to physics was that he could predict the motion. Oh, great. I was giving you the example of the moon. We're about to read that here in the book as well. For example, Newton's great contribution to physics was that he could predict the motion of comets, moons, and planets via his laws of motion once he knew the present state of the solar system. Right. Once you know the position of the sun, the other planets, the blah, 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 and you have laws of gravitation governing all of this, at the classical mechanical level, you can just predict the motion of a comet, a moon, or whatever at any given time into years ahead, actually, unless you've missed something, of course, unless you've missed a part of the equation, which could be possible. Say you miss some asteroid belt or something, which I think is unlikely because generally people do a good job with that. This is what NASA is doing. This is what NASA does, okay, even now. So what Newton did hundreds of years ago is still obeyed to the most part, given that you're in a classical mechanical picture, given that you're doing what NASA does. So NASA does this even now, even now. So it's still valid. It's still valid. It's just that's not quantum mechanics, because quantum mechanics has to do with smaller things. For centuries, physicists had marveled at the precision of Newton's laws, that they could predict the motion of celestial bodies in principle millions of years into the future. So see how physics historically was very deterministic. Physicists are a little bit like control freaks at this point. At this point in history. Now they cannot be because they know quantum mechanics. But at this point in history, in the 1920s and 1930s, people are used to being able to predict the position of, as I was saying earlier, physics in a nutshell is trying to just say, what is the position of a thing as a function of freaking time, right? Just tell me x as a function of t, please. That's what physicists kind of want to some extent, or to start. Later on, we want more things, but that's kind of what we want to start with. And not only that, we're so obsessed with wanting to know this, we want to predict this for a thing of interest, say our moon or the Jupiter's moon or whatever. We want to predict this for millions of years into the future. And this is called deterministic physics or classical physics, which was good, and it gave us results at that point, and that's all we knew. The fact that suddenly now you have things when you measure them, you don't know their something anymore, their velocity anymore, or their position anymore, or something stays uncertain at all times. This is very new, and this is very upsetting to physicists who are historically control freaks of nature. In fact, up to that point in time, all of science was based on determinism. That is, a scientist can predict the outcome of an experiment if the scientist knows the position and velocities of all particles. Like, all you had to know was the position and velocities of all particles, and then you can just write down this system of particles deterministically forever. That's what physicists were used to. But now you're saying at the small stuff level, like electrons, as soon as you measure its position, now you don't know its velocity. What will you do now, physicist? What will you do now? Followers of Newton summarized this belief by comparing the universe to a gigantic clock. God wound up this clock at the beginning of time, and it has been steadily ticking ever since, according to Newton's laws of motion. If you knew the position and velocity of every atom in the universe, then you can, via Newton's laws of motion, calculate the subsequent evolution of the universe with infinite precision. However, the uncertainty principle negated all of this, stating that it is impossible to predict the future state of the universe. There you have it. You can't control everything. That's what we're saying now in the 1930s or late 1920s. Given a uranium atom, for example, one could never calculate when it will decay, only the likelihood of its doing so. In fact, even God or a deity did not know when the uranium atom would decay. So, when you got into the atom scale of things, or inside the atom subatomic scale of things, you no longer could just predict things deterministically forever. This was not a thing anymore. You had to live with probabilities, you had to live with uncertainty. And some people say that if you can if you can deal with uncertainty, you must be smarter. And sort of that kind of thing happened to the physicists at that time. They had to be smarter now. They couldn't just do everything the classical way. They couldn't just do everything the classical physics way, where you could just predict something forever. No, you had to accept that there's uncertainty. You had to accept that there is a probabilistic approach needed for understanding quantum mechanics. And quantum mechanics stands on probabilistic nature. You have to be okay with probabilities all the time now. The entire field is all just probabilities, So this whole way of thinking, this whole way of doing the math, that's why there's a whole new field now of quantum mechanics. As I was saying, in undergrad, they're taught in different years. They're not the same. It's not the same. You don't do planets and comets and sun and stars and all that anymore in the quantum mechanics class. You did that all in classical physics, or if you took an astrophysics class, astrophysics is mostly all classical, thank goodness. So a lot of astrophysicists, for example, they don't necessarily bother with quantum mechanics because, if their systems are mostly obeying classical mechanics, they're good with that. Now, of course, if you get into particles and want to understand physics of something happening in an exotic environment like a gamma ray burst or something, and you are interested in the particle interactions in there, then you might want to know some quantum mechanics, just because at the particle level, you would need some quantum mechanics. But if you're interested in classical scales, then you don't really need quantum mechanics. So a lot of astrophysicists are happy that they don't need quantum mechanics. They can just take their classical physics. They can take quantum mechanics, but never have to use it again and just go on with their life. But with particle stuff, you need quantum mechanics. And I think in general, quantum mechanics is important, but it's newer. It's as you can see, it's about 100 years old. It's about 100 or a little bit more than 100 years old. It's not like 200, 300, 400 years old. It's still developing, I would say, to an extent. So it's an exciting time to be part of quantum mechanics because it's only 100 years old, okay? You can contribute to it as well. In December 1926, responding to Born's paper, Einstein wrote, "Quantum mechanics calls for a great deal of respect, but some inner voice tells me that this is not the true Jacob. The theory offers a lot, but it hardly brings us any closer to the old man's secret. For my part, at least I'm convinced that he doesn't throw dice." So this is where that quote comes from. God does not throw dice. As in, all of this probability stuff was irking people like Einstein, who is like, you're saying that we have to live with probabilities and uncertainties, and we measure probability and we measure uncertainty, and that's our answer? Like, that's the measurement? That's what we measure. Yeah, that is the answer. That's what we measure in quantum mechanics. So it's like God threw dice, and we are happy with it. When commenting on Heisenberg's theory, Einstein remarked, "Heisenberg has laid a big quantum egg. In Göttingen, they believe in it. I don't." Schrödinger himself disliked this idea intensely. So, wow, Schrödinger's the one who wrote the wave equation initially. And then once it became a probability thing, I guess he didn't like it. He once said that if his equation represented only probabilities, then he regretted having anything to do with it. Aww. Einstein chimed in that he would have become a cobbler or employee in a gaming house if he had known that the quantum revolution he helped to initiate would introduce chance into physics. So, this is how much they loved determinism. This is how much they liked being able to predict the future. This is what they thought their role was. You understand? Like, this is going against the identity of physicists because they thought their role as a physicist was to be able to give predictions and deterministically predict the future and just tell you what will happen with an equation. But physics is more than that, nature is more than that. And sometimes it can give you an identity crisis because nature is saying, no, you cannot measure me and be certain about everything at the same time. Just suck up to it. Suck it up, buttercup, is what nature is saying, as with quantum mechanics. Is that no, there will be only probabilities. You won't know everything deterministically forever. No, no, no. You can't predict everything for at every scale deterministically. That's just not how physics will work. Physicists were beginning to divide into two camps. Einstein led one camp, which still clung to a belief in determinism, an idea that dated back to Newton himself and had guided physicists for centuries. Schrödinger and de Broglie were allies. The other, much larger camp was led by Niels Bohr, who believed in uncertainty and championed a new version of causality based on averages and probabilities. Bohr and Einstein, in some sense, were polar opposites in other ways. While Einstein was a child, shunned sports, and was glued to books on geometry and philosophy, Bohr was renowned throughout Denmark as a soccer star. Whereas Einstein spoke forcefully and dynamically, wrote almost lyrically, and could exchange banter with journalists as well as royalty. Bohr was stiff, had a horrible mumble, was often inarticulate and inaudible, and would often repeat a single word endlessly when engrossed in thought. Oh shit, I can't repeat myself. Maybe that's a thing. While Einstein could effortlessly write elegant and beautiful prose, Bohr was paralyzed when he had to write a paper. It got so dark because the sun set. As a high school student, he would dictate all his papers to his mother. Oh my God. After he married, he would dictate them to his wife, even interrupting his honeymoon to dictate one long and important paper. He would sometimes involve his entire laboratory in rewriting his papers, once over 100 times, completely disrupting the work. Wolfgang Pauli, once asked to visit Bohr in Copenhagen, replied, "If the last proof is sent away, then I will come." So Bohr, this is probably where we get the academic revisions from. We can blame Bohr. He believed in perfecting papers and rewrote them so many times that people were like, please tell us when you have your last draft because we can't be reading your 95th version. We know you have 5 more to go. That's too funny. Both were obsessed with their first love, physics, Einstein and Bohr. Bohr, in fact, would scribble equations on the goalpost of a soccer game if he had an inspiration. Both would also sharpen their thoughts by using others as sounding boards for their ideas. Strangely, Bohr could only function if he had assistants around him to bounce off ideas without an assistant whose ear he could borrow. He was helpless. Wow, okay, interesting. Some people are like that. They need somebody to sound ideas off of. Ole Barbie, Shona Pucci. Oh, Shona Pucci, Shona Pucci, Shona Pucci. Ole Barbie, Shona Pucci. It's my baby. It's my baby. The showdown finally came at the so remember Einstein is not liking that Bohr has said that it's all probabilistic. Quantum mechanics cannot be done deterministically by nature. Intrinsically, it is a probabilistic theory and study. It's not a deterministic study as is classical mechanics. You cannot deterministically just say the position and velocity of an electron like you would for, say, the planets. Not the side eye from the cat. Yeah, seriously. So the showdown finally came at the 6th Solvay conference in Brussels in 1930. What was at stake was nothing less than the nature of reality itself. Einstein hammered incessantly at Bohr, who reeled under the constant attacks. Oh gosh. But managed to ably defend his positions. So remember, Einstein was a very good speaker. So I can see how he would have made Bohr look bad. Sometimes people that are more successful, not saying that Einstein wasn't extremely clever, he was, but sometimes people who are better speakers can actually be more successful just because they can communicate their ideas. And because their ideas are communicated properly, then those ideas get propagated and they go on to become something more successful. Other people can also contribute and it becomes a whole thing. Whereas if you cannot communicate, then your ideas could just die before they're even a thing. So, poor Bohr. But yeah. In Einstein's case, he was a great scientist as well as a great communicator. I feel like that's why at this point we consider communication of science as a part of science, because without it, really, you're not going to be able to establish anything, you know? So it might as well be an intrinsic part of science. I have to get going. Actually, have something I have to get to. We are still on this chapter covering the unification. It's also gotten really dark because in Boston the sun has already set, even though it's only like 4:30. We're on this chapter that covers unification and the quantum theory. We're basically covering all the developments of quantum mechanics in the 1920s and 30s. Oh, their food. Oh my God, I'm stuck in the sofa, but their food is about to fall. Hi. Oh, okay, yeah. So, oh gosh, my legs are stuck. They're over there. Thank you, Heike. Thank you so much for being here as always. But yeah, we will pick up from this part of the chapter, and I might even repeat this a little bit because we didn't have everybody here today. That's usually part of the physics study. But basically, we are still on the same chapter. It's called Unification and the Quantum Theory. We're basically looking at developments in quantum mechanics in the 1920s and 1930s, which still could have the influence of people like Einstein, of course, because he was around then, and people like Dirac, Schrödinger, Bohr, Niels Bohr. Those are the scientists whose work we're covering here. And this big development of needing probabilistic theory for nature was coming up in quantum mechanics, something that we had not really seen before in classical mechanics. So we will continue this next time. We'll cover this a little bit more, and then we'll continue the story here. This is part 3 of the book, Einstein's Cosmos by Michio Kaku. Thank you so much. Oh, thank you so much. Kayla said make sure you subscribe and you just learn new stuff. Oh, thank you, Kayla. Thank you, everybody, for being here. As I was saying, I will continue this part and kind of iterate the important parts that we just went through with quantum mechanics. Um, I'm also kind of developing an introduction to quantum mechanics of my own that I might be able to share with you soon, which covers some of these equations and things that we're talking about in a little bit more detail, which hopefully helps. But I know that the story and the narration way of doing it could also work in sense of like getting a sense for it, getting a feel of it. Um, yes, good night, everybody. Sleep well. Heike said, thank you for reading and explaining Cosmos. Happy New Week to Baji and science friends. Yes, thank you so much. Um, thank you for being here. This part has a few more pages left, not too bad. We've made a lot of progress and we'll continue on and we'll definitely finish this next time, which will be a very important part of physics that we would have covered at that point. And then the next part of this book is called War, Peace, and E equals MC squared. Some of that is, of course, to do with the atomic bomb. So not a very happy topic, but it is what it is. We are still in the midst of quantum mechanics initial progresses, so it's still all very fun and good. So we'll make sure to cover this comprehensively next time. Thank you so much for being here. I have to charge my phone before I start driving, so I'll go now, even though this has been really fun. Thank you so much for listening. Thank you for joining. Please do subscribe and like the live. It is like Warhol art book. I actually do from front, I mean. Oh, Warfront. It is like Warfront book. Yeah. Yeah. The wars, the wars were going on at that time. World War One and Two. It's basically going to be part of this. So, well, sort of, I don't know how much of World War Two will be part of it, but sort of, yeah. It's going to be showing up. Yeah, unfortunately, E equals mc squared and the mass energy equivalence that we get from special relativity also means that we get an atomic bomb, which of course was very destructive in World War II and whatnot. So I think there is a story with that too that we will cover here. But before that, we will finish up the quantum mechanics discussion. Campbell, Andy, Warhol, Bean, Can. Oh, wait, are you talking about... I don't know what you're talking about. Maybe I just don't know what that is. Sorry. Yeah. So anyway, what day is today? Is it Sunday? If today's Sunday, I'll try to pick this up soon here, maybe next couple days and finish this up. I think I'll do it later at night, one of these days soon, so that most of our physics crowd can join and catch up with the topic. Today I did this afternoon live because I've got somewhere to go and come back and all that stuff. So, but yeah, thank you so much once more for being here. Have a great rest of your Sunday or Monday, depending on where you're joining from. Marilyn Monroe art by Andy Warhol. Oh, okay. I'll have to look into that. Marilyn Monroe. I do know who that is, sort of. Um, yeah. Yeah. But yeah, thank you so much once more for joining. Thank you for supporting the channel. Please do check out our other videos, shorts, live streams. If you want to hear about the topics that we've covered from this book and also in general from my discussion in previous live streams sort of related to this, you can just go back to the channel under the live tab. You can find all of the live videos that have been uploaded after the live stream. So you can catch up on the discussion there. You can hear about our special relativity chats and discussion as well in the past live streams. And yeah, thank you for listening. Thank you for being here and watching and enjoying the kitty cats and hanging out. Thank you. Bye bye. Thank you and see you next time. Bye.